Question number 14 is a conceptual question again. For the following cylindrical pressure vessel, what is the angle of orientation for the normal stress perpendicular to the weld if sigma equation is used for stress transformation? So again, it's about that two summary page that we discussed, and that is what is the theta that we should use here. Note that it says that use sigma n into this problem, in this equation. So let me take out an element like this. When we say sigma n, it means that we need to consider either the left or the right plane, and we need to rotate that toward the welding. In that case, how much is the angle? Angle would be 30 degrees. Positive or negative, because we have both of them here. That should be clockwise, so clockwise is negative, so I will consider that one. Question number 16, the problem says axial stress in a thin-walled spherical pressure vessel is given by which of the following equations? Sigma A for sphere is PD over 4T or PR over 2T, so that would be option B. Question number 17 and 18, again, they require some calculation. I will leave it for later. Question 19 is another conceptual question. For this vessel, the stress in the x direction is hoop stress, longitudinal stress, shear stress. So this question actually competes with that question that we just talked about. Stress in the x direction is hoop, because that is circumferential in that. Question 20, spherical gas storage tank with an inside diameter of 16 meters is being constructed to store gas under internal pressure of 1.75 megapascal. The tank will be constructed from structural steel that has a yield strength of 250 megapascal. If a factor of safety of 3 with respect to the yield strength is required, determine the minimum wall thickness required for the spherical tank. I believe we have similar questions as a practice question in the class. We have one sphere. Internal pressure causes tensile on the body of that, on the wall of that, and we want to see how much would be required thickness. So we need to determine how much is the stress caused by that internal pressure. So that would be PD over 40, and this one should be smaller than the allowable tensile stress of that seal, which is yield stress divided by the factor of safety. So this is the design equation that we have. Everything here is known but the thickness, and we can solve that for thickness. Let me plug the values. The internal pressure is 1.75 megapascal. The diameter of that sphere is 16 meters, which means 16,000 millimeters. And the thickness is what we are looking for, and that should be smaller than the yield stress, which is 250 divided by factor of safety of 3. And if I solve that for T, that gives me T should be larger than 84 millimeters. So that would be option 20. Okay? All right. Question number 21 is kind of difficult question. It's a tricky question. It doesn't look so, but it's a bit tricky. Spherical rubber balloon is blown up until its diameter is 3 times the initial diameter. If the modulus of elasticity is 9,000 psi and the Poisson's ratio is 0.44, determine the stresses in the balloon. Assume the stress-strain behavior is linear. The first parameter that we need to determine is the strain. How much is the strain in that element? When we blew it up, how can we determine the strain? What is the definition of strain? Strain is change in the length divided by the initial length. Here, the length that we are talking about is the diameter. How much is the initial diameter? Say 1. How much is the diameter after blowing it up? 3. How much is the change in the diameter? 3 minus 1 is 2. How much is the strain? 2 divided by initial length. How much is that? 1. So that would be 2. Strain here is very large. So strain here is defined as 3 minus 1 divided by 1. Another point that is hidden in this problem is we are talking about sphere. Sphere has the same strain in all directions. Look at this sphere. If we have one element, we know that the stresses in perpendicular directions or strain in perpendicular directions are equal to each other. So the strain value that we have obtained at that point is actually a strain in any direction, any perpendicular directions. So let's say epsilon x and y are two perpendicular axes, and they are equal to the strain that we just determined, 2. And now I can use the generalized Hooke's law to determine stresses from strain. Again, here we are working with a thin element. And thin element means plane stress problem. So I will use the simplified equation of plane stress problem. And I will write it down like this. Sigma x is E divided by 1 minus nu squared plus epsilon x plus nu epsilon y. And that gives me 32,100 psi, which is equal to 32.1 ksi. The last two questions are about combined loading, the topic that we talked about. I will start from the bottom problem. A 2.5-inch diameter solid aluminum post is subjected to a horizontal force of 2.45 kips, a vertical force of 7.3 kips, and a concentrated torque of 10.85 kips inch. Assume that L is 3.5 inch. Determine the normal stress sigma y at point K. So the procedure for solving this problem is taking 3 steps. First, move all the forces to the cut section. Second, determine the section properties, and then determine the stresses. Here, we can simplify that. Why? Because here we are just looking for the normal stress. For normal stress, should I take care of the torque? Torque doesn't play any role, so just ignore that. Should I take care of the shear force? No. What about Q? None of them. So I will just focus on determining the axial force and the bending moment. Okay, without going further, can you tell me if there is any bending moment in that figure? There will be a bending moment, and that bending moment is caused by that shear force V. How much is that? That would be V times L. Which axis gets that moment? That would be about the z-axis. Should I take care of that when I'm determining stress at point, it looks for stress at point K. Okay. Should I take care of that? Yes, because stress is not 0 for that point. Okay, let's do that. So if we cut the section, we just need to take care of 2 forces, the axial force, which is P, and the moment, which is V times L. And the magnitude of that is 8.575 kips inch. And the magnitude of P is 7.3 kips. The stress caused by the axial force, is it positive or negative? Negative. What about the stress caused by that bending moment? Positive, following the direction of the moment. So I subtract them from each other. That gives me sigma equal to negative P over A plus MC over I. And I plug the values. Okay, how much is area? Pi diameter squared over 4. How much is the moment of inertia? Pi diameter to the 4th divided by 64. And I will get these two numbers, plug them back into this equation, knowing the P and M. How much is C for this problem? Half of diameter. So once I plug the values, I will get 4.1, which is 8. Okay? So as you can see, compare this with the problem that I asked you to practice in class, or the problem that I gave you last night to practice. These are much easier, but they are following the same concept. The point is, if we understand the concept, we would be able to quickly find the answer. Here you shouldn't be worried about the torque, we shouldn't be worried about Q, or any other things, because we just want to determine the normal stress. What would be the case if I want to determine shear stress at that point? Moment doesn't matter. Axial force doesn't matter. I will just take care of that torque and that shear force. Let's talk about that conceptually. How much is the shear stress caused by that V at point K? That would be 0. What is the axis of interest for that shear force? Z. If I want to determine Q for point K about the Z-axis, how much would be the area for the cut section? 0. So that gives me Q equal to 0. So the shear stress caused by that shear force is 0 at that point. Is there any shear stress caused by that torque? Yes. So that would be simply Tc over J. That's it. So if I will ask you to determine the shear stress in that problem, that would be even easier for this case. Question number 22 is again a conceptual question. It's a very important question. I remember I talked about this in one of the sections. This is a very easy question, but many students have difficulties with that. And the reason that I drew those three-dimensional figures and colored different faces of those boxes, those three-dimensional stress elements, was to understand this concept. A shear force is applied on the top part of that element. We want to see how the stress element looks like at that point without solving the problem. As you can see, in all these problems, there is a shear stress, so that doesn't help us. The thing that we need to take care of is if there is any normal stress, and if there is a normal stress, which direction is that? And is it positive or negative? So based on that, we can determine which option is correct for this problem. Once we cut this element, if we take out the element, I would see this three-dimensional stress element. The stresses, both shear and normal, are just acting on the top surface of that cut section. Because when we are talking about the stresses developed by combined loading, they are always developing or producing on the cut section of the beam. So here, what section is cut here? The top surface of that. Look at all the problems that we discussed in different sections, either today or on Tuesday. In all those problems, the surface that gets the stress is the surface which is cut. Here for this problem, I'm actually cutting from this point. Let me show it here. So I'm cutting that from this point, and if I cut that, the top surface is being cut, which is the green surface. And regarding that fact, there is not any normal stress in the horizontal direction. So A, B, and C are not an option. The only possible options are D and E. How can I determine which of these two is correct? It depends on the direction of the moment. Again, use the right hand rule. Put the hand fingers aligned in the horizontal direction going to the left. Bend your fingers toward downward. Where the thumb goes? It goes out of plane. What kind of stress developed on the right side of the neutral axis? It causes tension on the right side of the neutral axis and compression on the left side. Let me show it here. The moment that is developed is like this, and it causes compression on the left and tension on the right. So based on that, the only possible option would be E. We should say why there is any stress, because we shouldn't prove that why there is not any stress. We should see what is producing a stress at that point, because if there is not anything that produces stress, that part should be stress-free. Look at that force. That force, when I cut, let me cut this section again. This is the cut section that we are talking about. When I move that force all the way to that cut section, there will be a shear force here and a moment that we discussed. What would be the effect of that shear force? What kind of stress developed by that shear force? Shear force produces shear stress. That's it. Do you expect to see any normal stress caused by shear force? So no. What kind of stress is developed because of moment? Normal stress. Does moment produce any shear stress? Now, we have these two forces, moment and shear force. Which surface gets the stresses produced by these two forces? Is it the top surface, the side surface, or the front surface? Let me show that like this. Which surface gets the stress? We have green surface over here, red surface over here, and purple surface over here. Which surface gets that stress? The green surface, the cut surface. Always the cut surface gets the stress. So this is what I drew here. So there is not anything that produces stress in that red surface. Is there any? We do have shear stress, but that shear stress is actually indirectly produced by the stress that is initially developed on the green surface. I'm talking about the normal stress. Is there any force that causes normal stress in that red surface? No. So there should not be any normal stress in that direction. Is there any force that produces normal stress in the purple surface? So if you don't calculate normal stress in those surfaces, do not put anything over there. I understand that when we look at this problem, when we see a shear force goes the horizontal direction, we may guess that there should be a stress developed on this side. But when we talk about this mechanics of materials, when we go over all these steps, there is nothing to produce stress in that red surface with the cut section that we are studying here. So nothing. That would be zero. Does that make sense? Yes, ma'am. Case that we might see normal stress in that red surface would be the case where we have a force acting on this side and another force acting on this side. So in that case, we see compressive stress in that surface. Other than that, there is not any normal stress in that point. If there is just one side, no, there is not any normal stress on that side because that is actually moved downward by shear mechanisms, not by the normal stress. If I use the right-hand rule for that force acting on the top of that element, I should put my hand in the horizontal direction, face it downward. When I curl my finger downward, the thumb goes outward from the surface. It means that I would expect to see this kind of moment. And if we have this kind of moment, it produces compression on the left and tension on the right. And because this point is on the right part of the neutral axis, that gets tension stress. Now there are some other calculation-based questions. You can find the solution of these problems, exactly these problems, in the ebook. So this is one of those problems. A hollow shaft with an outside diameter of 57 millimeter and an inside diameter of 47 millimeter is subjected to torque T. The shaft is made of aluminum. Strain gauge is mounted on the shaft at the orientation shown in the figure. Theta is 30 degrees. If T is 900 Newton meter, determine the strain reading that would be expected from the gauge. So first, we need to determine how much is the stresses caused by that torque. That torque produces shear stress, and the magnitude of that is calculated from this equation, Tc over J. Torque is known. C and J depends on the diameter of that section, and we can determine that stress. Second, we need to determine strain from stresses. So we use the generalized Hooke's law to determine strain. Tau xy and gamma xy are related from that equation, and we determine gamma, but that gamma is the shear strain. We are looking for how much would be the expected reading in that direction. To determine that, we need to use the strain transformation equation. There is one fact about this problem. When we want to rotate that element and determine the strain along, the, say, the n direction, we need epsilon x, epsilon y, and gamma xy. But we have already determined gamma xy. Do we know how much is epsilon x and epsilon y for this problem? We know how much are those. 0. Why? Because there is not anything to produce normal strain in any direction. So those are 0. So I plug the values here and determine how much is strain in the angle of 30 degrees. So the question that we have in the exam is exactly like this. Strain gauge is mounted on the outer surface of a thin-walled boiler. We know the dimension of that boiler, including the external diameter and the wall thickness, also the modulus of elasticity and the Poisson's ratio. We want to determine how much is the internal pressure in the boiler if strain gauge reads a certain value. To answer that problem, we need to use the strain in the pressure vessels, in the cylindrical pressure vessels. Strain in the cylindrical pressure vessel is a function of internal pressure, radius, thickness, and the material properties. Look at this equation. Everything is known but internal pressure. So I plug the values and I solve that for P, and I can determine how much is P. The very last question. The delta rosette mounted on an outside of a cylinder compressed air tank. The metal has a modulus of elasticity of 125 gigapascal and the Poisson's ratio of 0.32. The inside diameter is 800 millimeter and the wall thickness is 11 millimeter. The strain measured in the gauge are 168 and 630 for B and C. How much is the air pressure in the tank? So this is a combined problem for strain rosette and pressure vessels. The answer to this problem is very easy. Let me ignore all these parts. We know how much is the longitudinal strain. We have a formula for that. So for cylindrical vessels, in the longitudinal strain is PR divided by 2TE times 1 minus 2 nu. Epsilon A is exactly the longitudinal strain because we have directly measured that. So I can equal that to epsilon A. So epsilon A is known, radius is known, E is known, thickness is known, modulus of elasticity is known, and I can directly solve that for P. Okay?